Hello and welcome to the poster presentation of DCIM, Acoustic Channels for Data Center Infrastructure Monitoring. In the upcoming talk, I will present the results from research conducted by myself, Lars Wüstrich, and my co-authors Sebastian Gallenmüller, Marc-Oliver Pahl, and Georg Kahle. Data centers are at the core of our daily lives. They often run in the background of applications, they store information or make computations, of which the results then get delivered to us. In case of an outage, many applications that we take for granted would simply stop working. And therefore, due to their importance, operators of data centers implement meticulous monitoring. The monitoring itself consists of several components that observe device states, network communication, and the infrastructure of a data center. While device states and network communication can be monitored from within a system, infrastructure monitoring often requires additional hardware to measure the physical environment of data centers. We propose a novel method to monitor data center devices and infrastructure monitoring based on acoustic side channels. Our experiments indicate that the proposed approach enables activity detection of single devices in a mixed signal and even the detection of error beep codes emitted by a server board. Data center infrastructure monitoring can and often does include multiple side channels to measure the physical environment. The related work we identified also reflects this. The most commonly used side channels are power consumptions and heat. However, some other related work also considers monitoring other physical features like airflow, humidity, and vibrations, for example, of server cabinets. These measurements of such side channels has often some drawbacks. The measurements often have some low sample rate or resolution and may require expensive hardware. And we propose to use acoustic side channels as an additional source for infrastructure monitoring to support the infrastructure monitoring. Sound has many advantages. It's a byproduct of many physical activities, and many data centers devices emit sound anyways, for example via their onboard fans for cooling. Sound is also already well researched from other domains and can be captured with high resolution and sample rate, which enables accurate monitoring. Finally, sound is easy and cheap to capture, since microphones are low priced and can be easily retrofitted in any environment. However, to the best of our knowledge, there are no publications yet that would propose acoustic side channels to monitor data centers. Of course, acoustic side channels also have their challenges, but the data center soundscape has a set of properties that make sound a good fit for monitoring devices there. The figure here shows the spectrogram of a recording in a real-world data center over a time frame. On the y-axis, we can see the frequency of the spectrum, and the brighter a color is over time, the more energy it carries, which we would then perceive as louder. What you can also see in this figure is a server that boots up in the background. So we can see here that there is a beep at the 6-minute mark. 6-second mark, and the fans of the server that spin up afterwards, going into a characteristic frequency which exists because there are already the same devices with a similar fan that are running in the background. What we can see here, also in the figure, is that the data center soundscape is relatively static. Now, devices in a data center operate under constant load, which also makes the emitted noise rather static. And since data centers are most often remotely monitored and operated, there's little human interaction, which can additionally produce sounds. And even though we have many devices that operate nearby, changes in sound from single devices stand out, as we can already see here. Changes in activity, however, in addition to that, do not only affect the whole frequency, but only part of it, as we can see with the fans, in which only part of the spectrum is affected. And in addition to that, we also have some characteristic frequencies that stand out, since we already have devices that constantly emit noise on them, for example, the fans that constantly spin. Now that we have argued why acoustic side channels are suitable for monitoring data center infrastructure, we also want to show how we can identify a device's activities in a captured signal that contains sound from many devices in proximity. In the beginning, we need to record sound in a data center, as we can see in the top left figure. And Our procedure then consists of 5 steps. We first perform a short-term Fourier transform from the captured mixed signal to calculate how much energy a single frequency carries in a short time frame and plot it over time to get a spectrogram as shown before. In addition to that, in the second step, we limit the frequency spectrum to the relevant frequency band that we would like to look at. As mentioned before, changes in sound often only affect a specific frequency band that is previously known. And we then know how much energy a single frequency carries over time. And we can see the result of this step in the top right figure. The signal then, or the signals, come from all devices in proximity. And since we identified that the data center soundscape is relatively static, we can simply consider energy on all frequency and identify changes in the general soundscape to detect activity. And we do so by using the root mean square energy for each time frame of the remaining frequencies that are left after limitation. To calculate the root mean square energy, we sum up all energies of all frequencies that remain into a single value and calculate the radical of it. And we do so, the value is, all of the frequencies are done by the power of 2. We calculate then the RMS energy for every time frame in the recording, which leads to the figure in the bottom left that shows the activity over time. What we can see here is that this signal is still very noisy. So in a fourth step is we average out the RMS energy values over time and to identify general trends that indicate activity of a single device. And the amount of smoothing here depends on various factors. So one would be the length of the activity we would like to detect and the number of frequencies that are considered after the limitation. And in the final and fifth step, we identify the activities in the changes of the RMS energy. In our case, we apply a threshold-based method, but there are several possibilities to realize this step. In this example, we identify the start and the device turning on, of a device turning on and spinning up its fans. And these are marked by the dotted and dashed lines here. And we mark them as well in the other figures for clarity. However, now that we have seen that this procedure can already work for activities that span over multiple frequency, but we can also apply this method to detect single frequency event like beep codes. In this case, we limit the frequency band to the one on which this onboard buzzers emit sounds. And here in this example on this frequency. And since the RMS energy only has the energies from this very narrow frequency band, we reduce the amount of smoothing in the fourth step because there are less frequencies that carry noise. The measurements here show a buzzer that makes a sound around every 1.5 seconds for half a second, which is the result of a faulty fan on the server in the data center. So to sum up, we have shown that acoustic side channels are suitable to identify device activity in data centers, even though the captured signal usually contains sound from many devices in proximity. However, due to the unique properties of the data center soundscape, our methods work still very well to identify different activities and types of events. In the two experiments that we presented, we've shown that our approach works for activities that span over many frequencies, and we can even detect arrow beat codes from server boards which are on a single frequency. In the future, we will further research the possibilities of our method. We will look how robust it is regarding to different aspects, for example, multiple devices performing actions at the same time, or different types of noise in the background. Other potential fields are the device identification, where the exact frequencies that a buzzer makes of a device to identify it, or correlate device activity with management traffic, for example, via IPMI. And finally, if we have multiple microphones that can capture the same event, we would like to look at the triangulation and device identification via this method. So if you have more questions, please come by our poster, and we're very excited to discuss with you about our research.